Hey everyone, welcome back to the channel. In this video, we're going to look at A2 level physics formula. Basically, all the formulas you need to know before you sit for your A2 paper. So without further ado, let's get started. Chapter 1, Motion in a Circle. So the first formula is arc length formula. So this formula will come in handy when you want to define a radian. Because sometimes in exam they'll ask you to define what's a radian. And if you make theta as a subject, theta equals to S over R, because the theta here is in radian. And we know radian means angle subtended at the center when the length of the arc is equal to the radius of the circle. So when they ask a radian, they specifically ask a radian. A means basically 1 radian. Yeah, so knowing this formula will come in handy when you want to define it. Okay. Next one is angular velocity, which is angle turned through per unit time. Then we have velocity equals to r omega. Then we have omega, which is the angular frequency, equals to 2 pi over t for one complete oscillation. I say one complete oscillation because one cycle, it's 2 pi, right? One complete cycle. So that is why it's one complete revolution. Then another way to define angular frequency is it's equals to 2 pi f, because f is equals to 1 over t. So when you sub in f with 1 over t, you'll get 2 pi f. Yeah. So angular frequency and frequency aren't the same thing. So this formula proves that it's not the same thing. This is angular frequency. This is frequency. Okay. Then we have period. Period, you just rearrange this formula. You can get 2 pi over omega or 1 over frequency. Alright, then we have covered this. Frequency is equals to 1 over t. Then we have centripetal acceleration. A equals to v squared over r, something that I think we've known before in IG or SPM. Then this one we have r omega squared, which is something new that you have learned. Next, lastly, we have centripetal force, which is mv squared over r, and it also equals to mr omega squared, because v squared over r is your acceleration. Therefore, you sub in this inside the formula here, you will get mr omega squared. I would suggest you to know both of these for acceleration and both of these as well for centripetal force, because you don't know which information you will get in exam. Sometimes they give you velocity, okay, then you can just use this formula. Sometimes they give you omega, then you have to use this formula. Yeah, so you need to use the formula depending on what the question requires you to use. Okay, so that's about it for chapter 1. Let's move on to chapter 2, gravitational field. So the first one, it's very famous law, Newton's universal law of gravitation, where gravitational force equals to a negative g(mm) over r squared. G is your gravitational constant, which is given in your data booklet. This one right here. Oops. Yeah, this one right here. Then we have m, which is the mass of a planet, and the small letter m is the mass of another planet. Then r squared is basically the distance between the center of one planet to the center of another planet. Don't forget to square. Okay. Negative means attractive force. The second one, we have gravitational field strength. G equals to force per unit mass. This one, I think you're familiar with the formula weight equals to mg, right? So now instead of weight, we just use F equals to mg. But both are the same thing. Then another way to write gravitational field strength is negative gm over r squared. The g is still same, your gravitational constant. M is the mass of the planet and r is the radius of the planet. Okay. The third one, we have gravitational potential, and this is equals to negative gm over r, just r, and it is not squared. Good thing is, it is given in exam. These both, the one that are highlighted in green, both are given in your exam, basically in your formula sheet, the second page. So this, your g is still the same, gravitational constant, m is your mass, the planet, r is the radius. Then next one, we have gravitational potential energy, which is negative gmm over r. You have two masses. One is the mass of one planet and another one is basically the mass of the other planet. Or you can also write it as m phi, because gravitational potential is negative gm over r, and potential energy has extra mass here, which is basically the mass of a test mass. People usually say it as the mass of a test mass because gravitational potential energy is work done to bring a mass from infinity to that point. That is gravitational potential energy. Gravitational potential is just work done per unit mass. Is per unit mass from infinity to a point. Potential energy is bringing a mass. Yeah. To take the mass, you can just stand by your potential equation. You can find your potential energy. Okay. Alright. Then, next one we have escape velocity. So, this is escape velocity formula. I know you might not be familiar with this, but it's actually the same as what we have learned before. Because I know escape velocity formula, you see it as V E equals to 2gm over r square root, right? So the difference is now, we know g is equals to gm over r square from this here, right? Okay. So now, how can we relate this and this together? We have gm over r here. So let's try to take out gm over r. So making gm over r as a subject, can make it as a subject, you will get gr. Because you bring this 1 over r here, you will get gr. Am I right? So when you substitute gr inside here, you will get square root 2. Gm over r is gr, right? Gr. So that is how you get this formula. If you can remember this, just stick to that. It's the same. Or you want to remember this, it's also okay. Stick to whatever you're familiar with. Yeah. Okay. Then the last one, which is the Kepler's law. I believe we need to know how to derive this Kepler's law. So how you start the derivation is centripetal force equals to gravitational force. Then you equate them, you derive, then eventually you'll get T square equals to 4 pi square over gm times by r cube. So g is your gravitational constant as usual, mass is the mass of the planet, t is the period, r is the radius of the planet. So why is it Fc equals to Fg? Basically, why is it centripetal force equals to gravitational force? Because when something is in orbit, centripetal force is caused by the gravitational force. This is actually Kepler's third law. Yeah, and you should also know the what we call the relationship where T is actually T square is proportional to R cube. Yeah, this is something that you should know as well. Okay, let me erase all this. Alright, now the third chapter, ideal gases. Ideal gases is quite a famous chapter as well. First formula, PV equals to nRT. P is your pressure, V is your volume, N is your number of moles, R is a gas constant. It's given here. Okay, let me highlight here. Gas constant. In your data booklet lah. Okay. Then we have PV equals to NKT as well. So NKT is basically number of molecules. Another way to write it, K is your Boltzmann constant. Boltzmann constant is also given here. That's your Boltzmann constant. Yeah. Okay. Then the next formula we have number of moles, N, the small letter n equals to the capital N, which I said before, number of molecules or particles, divided by Avogadro constant. And this formula here is number of moles equals to mass over molar mass. Mass of the gas molecule, molar mass of the gas molecule. Usually you use this formula when they already specify what type of gas. If let's say they say nitrogen gas, then they want you to find number of mole, for example. You can use this if they give you mass of the nitrogen gas and the molar mass of the nitrogen gas. Chemistry student is probably familiar with these two formula because you use them a lot in your moles calculation in chemistry. Alright, moving on, we have the general gas law. This one can only be used when your number of moles is constant. Okay? You can only use this formula. Basically, for example, this is probably before, then they ask you to find the final pressure. Regardless, make sure a number of moles is constant. This is something that you should take note of. Okay, and actually this one PV over T is actually equals to a constant. This constant value is actually your universal molar gas constant, which is this one, 8.31. Yep, so that is a few things you should take note of. Next is PV equals to 1 over 3 Nm root mean square speed. P is your pressure, V is your volume, 1/3, N is your total number of molecules, M is mass of the molecules, and C is your root mean square speed. Okay, this is given. Good thing, that's the best part, is given. Moving on, we have half M root mean square speed, which is basically your kinetic energy, equals to 3 over 2 kT. So how do we get this? It's actually from this part here. You know PV equals to 1/3 Nm root mean square speed. Wait, I just realized I said it wrongly. This is not root mean square speed. This is not root mean square speed. This is mean square speed. This is root mean square speed. When you square root your mean square speed, you get a root mean square speed. The one we just see square, and this means mean. The two brackets in front means mean. This is mean square speed. Sorry, I just realized. I feel like, why am I saying something wrongly? Yeah. Then you know another formula is PV equals to NKT, which we just see here just now. So you equate them both, your N will cancel out, right? So that is why there's no N in this formula. Then you divide 2 both sides, you'll get half one side and 3 over 2 another side. Okay, you know what? I'll just show you. PV equals to 1/3 NMC square. PV equals to NKT. Right? So you equate both one. Cancel. KT equals to 1 over 3 M mean square speed. You bring your 3 the other side first. 3 KT equals to M mean square speed. Then divide 2 both sides. You'll get this, which is exactly the same. Okay. The next one we have average kinetic energy of molecule. We have discussed earlier. Exactly same as your kinetic energy formula, actually half mv squared, just that your speed now is called mean square speed. Then total kinetic energy is 3 over 2 nkt. Here there is n. Here got no n. Why here got n? Because they're asking for total kinetic energy. Total means you must include a total number of gas molecules. Okay. Then lastly we have total internal energy, which is also 3 over 2 nkt. So in the next chapter, which is in the thermal properties of materials, you will learn that internal energy is also equivalent to kinetic energy plus potential energy. And since ideal gas has no potential energy, your internal energy is just equals to kinetic energy. That is why it's just 3 over 2 nkt. Okay. Alright, nice. The last one is now only you have root mean square speed, which is basically you square root your mean square speed. Okay. Alright, so that's about it for chapter 3. Let's move on to chapter 4. Chapter 4 is just very little formula. It's called temperature. We have the first formula here. This one, in case they give you a thermometer and they give you some lengths and they ask you to find what is the temperature at probably this point. So you have to know this formula to calculate it. Okay. Then this one is basically converting Kelvin to degrees Celsius. If you want to get degrees Celsius by your temperatures in Kelvin, you minus 273.15. If you want to get Kelvin from degrees Celsius, you plus. So Celsius to Kelvin plus 273.15. Kelvin to Celsius, you minus 273.15. Okay, now chapter 5, thermal properties of materials. First equation is heat capacity equals to heat energy divided by change in temperature. Then we have specific heat capacity, which is more specific, which is amount of heat energy per unit mass per unit temperature change. Then we have latent heat, which is the heat energy divided by the mass. So latent heat is basically change a substance from one phase to another phase without change in temperature. That's why there's no temperature in the equation. The next one we have specific latent heat of vaporization. So vaporization means phase of substance from liquid to vapor. So since it's specific, so it's amount of heat per unit mass. Then fusion is solid to liquid, which is also the same formula, heat energy per unit mass. Also bear in mind, vapor to liquid is also vaporization, liquid to solid is also fusion. It works vice versa as well. Okay, alright. Then we have heat energy is equals to power times time, which is also equals to VI times time. Now, what is this formula about? So this formula is when they give you an experiment and they ask you to answer question based on the experiment. Solve some calculation or do some calculation based on the experiment. For example, they ask you to find the specific heat capacity of a copper block, and they show you what we call a heater, basically attached to the, not attached I would say, basically a heater in the experiment that they use, and they want to find the heat energy. So the heater, they mention the power of the heater. So with that information, to find your heat energy, you take your power times by the time. Or you take VI, because power is also equals to VI, right? So you take P equals to VI times by the time. So it depends on what the question gives you. If the question gives you power, then you use power. If the question gives you voltage or current, then you use current to solve this. Okay. So this one is usually when they give you an apparatus to determine the specific heat capacity, and then they have the immersion heater, metal block, they have the thermometer, they have the insulation, the voltage DC power supply. Sometimes they'll have a voltage here at DC power supply, then something connected to an immersion heater, then we have a thermometer, something like this, right? For example, your experiment to determine the specific capacity. Then you use this formula. Okay. Alright. Then we have first law of thermodynamics. So first law of thermodynamics basically means internal energy equals to the heat energy plus work done. But the thing is, you need to know when to use plus, when to use minus. When to use plus here and when to use minus. And also for heat energy, when to use minus, when to use plus. So positive means, positive heat energy means the heat energy is absorbed by the system. If it's negative means it is given off by the system. Work done positive means you are doing work. Work is done on the system. You are doing work, so you are adding energy on the system. If it's negative work done, then it's work done by the system, because the system is doing work, so the energy is slowly decreased. That's why you call it negative. Internal energy, positive means the system gains internal energy, negative means the system loses internal energy. Okay. Next formula we have, at constant pressure, work done equals to pressure times by change in volume. Then we have at constant volume, your work done is 0. Why work done is 0 at constant volume? Because work done is equals to pressure times change in volume. So if your change in volume is 0, basically because it's constant volume, that means your volume is not changing, ideally your whole equation becomes 0. That is why your work done equals to 0. And another equation is internal energy is also equals to PE plus kinetic energy. Remember I mentioned somewhere here, right? Yeah. Sometimes they'll ask you to define this, or they'll ask you to describe a motion. Basically we have, for example, a rubber band. So what is the internal energy? Is there PE? What type of PE inside our elastic potential energy? Yeah, something like that. Okay, next chapter, chapter 6, oscillations. So this one we have covered before, right, in the few previous videos, few weeks ago. But no worries, we'll go through it one by one. But also bear in mind, oscillation does not only involve simple harmonic motion. It's just that most of the formulas in oscillation, almost all of it, revolve around simple harmonic motion. There's also resonance and damping, but very less formulas for it. Okay. Now, the first one, A equals to negative omega square x. A is your acceleration, omega is your angular frequency, x is your position at which any position that you choose. If you want to find the acceleration at that position, that is your x. Let's say you want to find what is the acceleration at x equals to 6. That will be your x value. Then we have frequency, which is equals to number of oscillations per unit time. This one we have seen before, and also this in the first chapter, right? Okay, now this equation, the trigonometric equation, where we have 3 types of trigonometric equation depending on where you start your oscillation. Okay? Then the next one, these 2 is given in your formula booklet. So basically this is the derivation of the first one, where you differentiate x, because when you differentiate x is dx dt, right? Dx dt is velocity. So when you differentiate this, you will get this. I know you might be thinking, how suddenly I get this? There's no a also in this equation. Okay. When you differentiate this, basically you differentiate this whole thing, you will get v equals to a omega cos omega t. Am I right? Yeah. Because first of all, you differentiate sine, you'll get cos. Differentiate the one in your bracket, you'll get omega out. So a omega is actually maximum velocity. So in the formula booklet, V naught means maximum velocity. Yeah. So it's actually the same thing. Both are the same. It's just that they give you this in exam, in the booklet. So it's up to you, you want to use this form or this form. As long as you sub in the right value. Okay. Then we have this one. The next one is V equals to plus minus omega square root a square minus x square. So a square is basically your amplitude, minus x square is basically which position you want it to be. Okay, and this also is given. Okay, let me just show you where it's given. Okay, so this is your formula booklet in page 3. So you can see here, velocity of particle in SHM. Yeah, so most of your A2 formula is actually in this page, page 3. Okay, the next one we have maximum velocity. This one, which is what I've discussed earlier, which is equals to omega times by your amplitude. Why times by amplitude? Because at maximum velocity, where is the position? It is at equilibrium. So that means your x is 0. Because at equilibrium, your x is 0. You're not moving, you're just there. So that is why when you make this 0, you'll get omega multiplied by amplitude. The next one we have maximum acceleration, which is negative omega square a, derived from this because maximum acceleration is at the amplitude. So that is why it's negative omega square a. Okay, let me erase this now. So the next part will be more clearer. Okay, kinetic energy is half m omega square a square minus x square. This is your mass of the object. Omega is your angular frequency, a is again your amplitude, and x is the position. Then potential energy, we have almost a similar type but not exactly the same. Half m omega square x. square. Then total energy is kinetic energy plus potential. Just add these two, you can get this. So I would suggest you don't memorize total energy. Total energy you know is kinetic energy plus potential. So in exam, just add these two if they ask. But if you can remember this, of course, it's a good thing. If you can't, I'm just giving you an alternative. Okay. So that's it for oscillation. Now chapter 7, electric field. Okay, so I just went and drink water a bit. Okay, now we can continue. Electric field. So the first equation, electric field is equals to force per unit charge. Next one we have electric field is also equals to potential difference over distance. So example, they give you plus, minus, is going down. So this is your D, and let's say they give you the potential difference, so you can use this formula. Okay, then we have Coulomb's law, which is KQQ over R square. Q is one type of charge, the small letter q is another type of charge. Probably one is positive, one is negative charge. Yeah. Divided by R square. This is similar to gravitational force, to Newton's universal law of gravitation, right? Yeah, similar. It's just that this one is charge. In Newton's universal law of gravitation, we use mass of the planet. Okay. Your K, this is your K, where 1 over 4 pi epsilon naught. So I just named this whole thing as K. Yeah, so this is also given in exam. Here. Not this formula, I mean the constant. Yeah. Can you see this? So given here. Yeah. Also, I want you to take note a bit. I know here I named the constant as K, because I just name it as K. In exam, if let's say you remember the formula as KQQ over R square, don't go and find for K in datasheet, because if you're going to find for K, you might accidentally sub in Boltzmann constant, so don't do that. I just name it as K, but I have always known that K is 1 over 4 pi epsilon naught, so I just straight away take this. I would never take this one. Yeah. If you think you'll get confused, use another value. Probably want to use W so that you know, so W is actually 1 over 4 pi epsilon naught. Yeah. Use which one, it's easier for you. Next one, we have electric potential, KQ over R. Same thing, my K is this. Q is charge, R is your radius as usual. Then we have electric potential energy, KQQ over R, or you can write it as QV. Basically, this V you times by another Q. So this tree is almost similar to Newton's law of gravitation. Yeah, not Newton's law of gravitation, sorry. Almost same to the forces you learn and the energy and potential you learn in the gravitational field. Gravitational potential is Gm over R. Am I right? Electric potential energy, it is not K, G M over R, or you can write it as phi m, right? And this one is QV, because this is equals to phi, and if you times by this by m, you're gonna get this, right? So same thing here. Yeah, so it's almost similar. Last one is electric field is equals to a negative potential gradient. This is something that you should know as well. Yeah, because I think if I'm not mistaken, they asked this in winter 2024 paper. Yeah. They asked what's the relation between the electric field and the gradient. So, make sure you know this. Okay. Chapter 8, capacitance. So, capacitance, I think 3 of it is given. Yeah, quite a lot in capacitance is given. Good news for you. Okay, so capacitance, the first one is equals to charge divided by potential difference. Next two is actually given in your exam. And this one is basically the opposite of calculating resistance. Because resistance in series, this is how you calculate. For resistance in series. And for resistance in parallel, this is how you calculate. But for capacitance, it's the opposite way. So take note of it. But the best part is you don't have to get confused, because both for the resistance and for the capacitance is given in exam. So yeah. Then next thing, energy stored in capacitor. We have E equals to half QV. Then this two is basically a modified version. You rearrange this formula, make V the subject or make Q the subject, and you sub in this, you're going to get these two variations. So which one to use? Well, that depends entirely on what the question wants. If they give you charge and capacitance, you use this. So it depends on what they give you. So this is the discharge of the capacitor. I put it as X equals to X naught, and that is what is also exactly given in your data booklet. Why am I saying it's booklet? It's data sheet, right? Yeah, it's attached to your paper. Where X could be current, it can be I equals to I naught E negative T over RC, where RC is actually your time constant. We put it as tau. Or X, it can be potential difference, where V equals to V naught E negative T over tau. Or it can also be charge. Q equals to Q naught E negative T over tau. Okay. Yep, so that's about it for capacitance. So you can use either three depending on the question. Next we have magnetic field. Okay, so this part of magnetic field, right, I wouldn't really say entirely it's in the syllabus, but just it's good to know. Okay, why I say it's not in the syllabus? Because this permeability of free space, specifically for magnetic field, like how you have one for electric field. What's electric field? Here, this one, there's also one for magnetic field. So it is not given in your data actually. So if they were to ask you, they should give you this value. And if they were kind enough, they should give you the formula itself. Yeah. So but rarely, even when I was studying them, I rarely use this formula. Almost never, probably like once. Yeah, but very rare you use this. So, but I'll just tell you and to know, this is permeability of space in the magnetic field. This is current. This is 2 pi, as usual. This is distance. So basically you have wire. This is the distance between the distance between the two wires. Then solenoid. This is permeability of free space again. Number of turns of coils around the solenoid, and I is current. Again, I say this one is very almost like never they ask, because if they need to ask, they have to give you this, because in the data booklet, it's like I say, it's not given. So almost I could say they should not be able to ask you this lah. But it's good to know. Just to know is just good to know lah. Yeah, but not need to focus too much on this. Okay, chapter 10, Electromagnetism. Force on a wire. We have this one, BIL sine theta. B is the magnetic field, I is your current, L is the length of wire, and of course sine theta. And remember, your magnetic field cannot be parallel to your wire. If your magnetic field is this way, so I put it this way, and your wire is also this way, you will not have a force, because you have no angle here, right? You have no angle, because if magnetic field is this way and your wire is this way, you can tell it's sine 90. But if it's parallel, it is sine 0. And sine 0 gives you 0, so you have no force. So be aware of that. Sometimes they can ask, what is the situation when there's no magnetic force? So one of the situation is when it's parallel. Okay, next one is force on a charge, where we have BQV sine theta as well. B is your magnetic field, Q is your elementary charge, which is this one. They actually name it as E here. Oopsie. Sorry. Yeah. V is velocity, and sine theta again, as usual, at an angle. Last one, Hall's voltage. Good news, this is given. Yeah, good news is given. So B is your magnetic field, I is your current, N is your number density, T is thickness, not time, yeah. Thickness of the slice of your superconductor, your semiconductor slice, and Q is your elementary charge. So T is thickness, yeah, not time. Don't get confused. Okay. Next one we have chapter 11, laws of electromagnetic induction. Too bad none of this is given. You have to know. First one is magnetic flux equals to BA. Then we have magnetic flux linkage and BA. So B is again magnetic field, A is area. Flux linkage is the same, just they have N, which is number of turns of coils. Then we have next one is our very famous, most famous law, which is our Faraday's law, because Faraday's law means the magnitude of induced EMF is directly proportional to rate of change of magnetic flux, right? Yeah. So this N is basically when there's turns of coils, and this is basically a magnetic flux. So that's why it's called rate of change of magnetic flux. And this is your EMF. Okay. Then this one, magnetic flux, if let's say it's at an angle, you use sine theta. Because if it's sine 90 degrees, you get 1. Right? Sine 90 degrees is 1. So that's why there's nothing here. But if let's say it's at an angle, just use sine, put in the angle value. Okay, next we have AC, alternating current. So we have the first formula is root mean square for voltage, which is the maximum voltage divided by cert2, square root of 2. And same thing for current, it's maximum current divided by cert2. Okay. Then we have average power formula. And since it's the average power, so we need to use V root mean square times by I root mean square. Ideally, P equals to VI, right? So this one is just become root mean square because we want to find average power. Then because we know V equals to IR, so you modify the equation a bit, then you can also get these two. But if you make I as a subject, you make R as a subject, and you substitute inside here, you can get these two variations. So it's the same like we learned in AS electricity, like I square R, V square or R. It's just that now it's average power, so we use root mean square. Another thing to note of is average power is also half of maximum power. So since it's half of maximum power, we can also use half times by the maximum power. So maximum power is V naught I naught, because maximum potential difference multiplied by maximum current will give you the maximum power. So same thing, if you modify this, you can get 3 different variations of the equation as well. So depending on what information the question gives, you can use it accordingly. Okay, then we have alternating current or voltage. What do I mean is the X and X are not here, can either be current or can either be potential difference. And good news is given in your exam as well. Alright, chapter 13, quantum physics, Einstein's favorite chapter, right? Yeah. So the first one is energy equals to HF. This one, I think you are quite familiar with this as well. Or there's another way to write it as energy equals to hc over lambda. E is the energy, H is the Planck's constant, F is basically the frequency, and C is actually speed of light in a vacuum. Okay, and lambda is the wavelength. Wavelength of what? Wavelength of your photons. Okay. And this E is also energy of your photon. Next one we have HF equals to minimum work done plus by half mv square max. What do I mean? This is maximum kinetic energy. HF ideally means your energy. So this is something you have to know as well. And next one we have this formula. So how does this formula come? Because if we draw the energy diagram, kinetic energy, frequency, you'll graph something like this, right? This will be your negative work done, which is your y-intercept. Your gradient of the graph will be Planck's constant. Then this one, if F naught, which is your threshold frequency. At this point, your KE is 0. So, your work done is equals to HF. So that is how we straight away get this formula. Okay. Then next we have intensity. Intensity formula is I equals to power over area, something we are familiar with. Let's change a bit, modify more. We have power is work done per unit time. We get this. Then modify even more. Work done per unit time is also energy per unit time. Work done is also energy, am I right? Then we add with number of photons to know the total intensity. So how many photons are there? Multiply it together to know your intensity. This is for photons. Next we have for electrons, where your current is charge per unit time. Therefore, you can also write it as number of electron multiplied by elementary charge divided by time. Okay. Next, we have your line spectrum. This is where your electron is jumping, right? So, for example, your electron is here. This is E1, is E2. So, initially, electron is at excited level, which is E1, and it's trying to come to the ground state. For example, at that point, your energy is E2. So, it's energy at excited level, energy at the lower state. Minus them. Let's say they ask to find the frequency. You can minus them. Use this formula to find your frequency. H is still again Planck's constant. Last one, the Broglie wavelength, where we have lambda, your wavelength, equals to Planck's constant divided by momentum. Okay. Right. That's about it. But too bad, none of this formula is given in your exam. Also, these two actually coming from photoelectric emission, that Einstein's theory. These two equations actually mainly. Yeah. Next, chapter 14, nuclear physics. Okay, so first equation, activity. So activity is rate at which a nuclei decay. So this is something you should know, dN over dt. Then finding half-life is actually ln 2 divided by lambda, where lambda is your decay constant. And the decay constant formula here is given in your exam. Good news, right? Then we have this one here, where X could represent activity, number of undecayed particles, or received current rate, depending on what the question wants you to find. Okay, yeah. Next, medical physics. Medical physics has quite a lot of formula, but only one is given. And this is given. Intensity reflection coefficient. This one is given in exam. So let's go through the rest. First one is attenuation of X-rays. This is your this is your transmitted intensity. This is your incident intensity. This is linear absorption coefficient. X is the thickness of the tissue. Attenuation of ultrasound has almost the same formula. The difference is, actually it's almost the same. It's just that K is absorption coefficient. It's the same. This is also absorption coefficient, right? Yeah. It's just one is X-ray, one is ultrasound. So both is the same. Now, next one, we have energy of 1 gamma photons in PET scan. There's a reason why I bolded 1. If they ask for energy of 1 gamma photon, you use this formula, where energy is equal to HF, which is learned in quantum physics, or mass of electron equals to C square equals mass of electron multiplied by C square, where C is the speed of light in a vacuum. Okay, if they ask for 2 photons, make sure you multiply by 2. Don't forget. Okay. Last one of this chapter, momentum of the photon, we have formula E over C, where C is the speed of light in vacuum and E is the energy of photon. Okay, last chapter in A2. A2 actually has quite a heavy part of A level, honestly. It's a lot of formulas to know and concepts to learn. But, of course, we'll do our best and see where that leads us, right? Okay. Last one, astronomy and cosmology. You have to know radiant flux intensity, L equals to 4 pi d square. L is your luminosity of the source. D is the distance between the star and the earth. And F is your flux intensity. Then we have Wien's displacement. It's a relationship where lambda max, which is your maximum wavelength, is directly proportional to 1 over thermodynamic temperature. So the experimental value of this constant is given as this one. Yeah. Okay. Yeah. So this one is related to a star. So maximum lambda is basically your wavelength emitted by the star at the peak intensity. So it's peak, so we call it maximum. And thermodynamic temperature is temperature at the surface of the star. And next we have Stephan-Boltzmann law and Doppler redshift. Both good news is given in exam as well. Yep. Doppler redshift for electromagnetic radiation. So Doppler we got learn a bit in AS as well. Yeah. Last one, Hubble's law is not given, but something's very easy to memorize. V equals to H naught D, where this H is your Hubble's constant. D is distance from galaxy to Earth, and V is the recession speed. Yep. So that's about it. We have come to an end of this video. I know this video can be quite long, but I hope you learn something new, or if there's any formula that you didn't know before or have forgotten, don't worry, just go back, revise a little bit, and you'll be good to go. Alright, thank you for watching, and I'll see you in the next one. Bye bye, and take care of yourself.